Right, so welcome back, and let's start building our applications up a little bit more fully than we have before. Okay, so in the previous weeks, we talked about how to kind of build the API, and we talked some basic concepts of how to kind of set up the database, how to harden the database, add encryption to it. And last week, we talked about how to add user accounts and have passwords done correctly. All right. So this is kind of what we were working on last time. All right. So today we want to build the front end of our system. Okay. So today we're going to add a web application to our API, and we'll talk a little bit more about authentication. So um, I'll spend quite a bit of today's lecture actually just kind of setting up the infrastructure and getting you familiar with how Ruby does front end with web applications. So there will still be some security content. Okay, great. So let's get started. Um, the first thing I want to talk about actually is about our APIs before we actually talk about our web application. So your API controllers are probably getting quite large. They're probably getting bigger and bigger and bigger and bigger because as you're adding new routes to the controller, it's just going to become a huge file, okay? And you'll find that it becomes really unwieldy to kind of make sense of what's in your API because it's just going to get really super long, especially in the coming weeks because students are asking me, hey, when are we going to update and delete resources and things like that? Well, as you start doing that, your routes, your control is going to become huge, okay? Um, so the first thing I want to show you is just, and this is optional, you don't have to do it, but I strongly suggest you do it, which is that with Rhoda, you can actually break your controller into multiple files, okay? And essentially, they'll all be of class API inheriting from Rhoda, but they will each understand that they are taking care of one set of routes, not everything, all right? And I'll show you quickly how to do that. Yes, question. We're not? We are. Yeah. Okay. Let me quickly take a check. Huh? Yeah. We are. We are. Okay. All right. Okay. So let's have a look at how to do it. Okay. So this is my new controller app.rb for this week. Okay. Your app.rb, and this is it. There's a little bit more in here than what I've shown, but this is largely it. All right. Actually, let me go find my actual route here and hold on. Let me go find my actual app.rb. This is it. Okay. And there's some stuff here that I'm not showing you, which I'll talk about later. Some security stuff in here, but otherwise, for the most part, this is it. So I've removed all the routes from my controller this week. Okay. And what I've done instead is I've added this plugin called multi-route. All right. I've added this plugin called multi-route. And what multi-route does is it tells Rhoda that this controller is going to be, the routes are actually going to be defined in multiple different, possibly files or multiple different classes. Okay. And then I begin as normal. The only difference is after I enter API v1, where I want to start splitting off into other files, I add this routing.multiroute. Okay, so I add this routing.multiroute. And this tells Rhoda, depending on which route is asked for after API slash v1. So after API slash v1, the next route, the next layer of the routing, consider all the other files that are available to you. All right. So now in my controllers directory, I have not only app.rb, I have an accounts.rb, I have an auth.rb, and I have a projects.rb. Okay. And I'll focus on accounts.rb and projects.rb because those are the routes I made last time. And essentially, this week, um, here is another controller file within the controllers directory called accounts.rb. And what this does is first it loads the primary controller file up here, okay? And then within this accounts.rb, I open up another API class. And this time, I start off by telling it, I am handling all the routes associated with accounts. All right. So basically, the multi-route, when it comes down here, says, okay, I'm looking for things within API slash v1 slash whatever comes next. I'm going to look at the other files to see where it is. And here it comes to the accounts route. So all my accounts route are now within this accounts.rb. Okay. And I can go ahead and start routing as if API v1 is already done and I'm in the next layer in. All right. So the next thing I look for then, so all these routes, for example, if I do a get route here, it'll be API v1 accounts slash whatever it is. All right. So using this technique, I can now split my controller into multiple files. Oh, this is wrong. This should be projects.rb. I apologize. Slide 2, could you help me fix that? This should be projects.rb. In projects.rb, similar idea. I start off by making sure I've loaded the primary controller first, so Rhoda knows that we're doing multi-routing now. Then I start API and I do the projects route. Okay. And then projects slash documents slash whatever we have. All right. So essentially now this allows me to split my controller. So all my accounts routes is in an accounts file, all my projects routes is in a projects file. All right. The name of the file is actually not important because when I'm loading all the files, I'm going to load all these files anyway. All right. What's just important is that each of these controller files first makes sure that the primary controller file is loaded first, so we know that we're doing multi-route we're doing multi-routing. Okay. And then each one of these will then start off by saying, these are the sub routes that I am going to be taking care of here. Okay. Are you okay with this? You can try it out, look at my code, try it out, play with it, read the documentation. And that's how we're going to do, that's how you can split up your controllers if they're getting too crazy big. All right. This is especially helpful if some of you on your team are working on some routes and others are working on other resources. All right. Great. Any questions on this? Are you okay with this so far? Yeah, question. No, it's not related to that. I don't think so. Yes, that you have not seen before. I don't think we did this last in my other class. Yeah, I know. I don't do all the techniques in one class because then the other class will become a total repeat of the. All right. Okay. Great. All right. So that's just some housekeeping stuff for your APIs. All right. So that you can start managing your APIs because you're welcome to start adding new routes and new resources and start building your projects out. You don't have to wait for me. You can now start building your projects out more fully. All right. But this will just help you get it under control. All right. That's the API. The other thing I wanted to mention is last week we started in the API, we started doing accounts. So you can check for usernames, passwords, stuff like this, correct? And also 2 weeks ago, I talked about logging. So I said anytime there's an error that is unexpected, especially, or suspicious, please log it. Remember we talked about that? Yes? We talked about logging, right? Okay. So today I want to remind you again, please be careful what you're logging. Don't, for example, like if somebody tries to log in and their username password doesn't fails, you can log that, oh, this person tried to log in and failed, but don't put their password in the log file, okay? And you may wonder why. The log file is kind of private. Yes and no. Treat the log file like your database. And I always keep saying, imagine your database is already compromised, all right? Imagine the world is reading your log files, because if anyone breaks into this server, they can read the logs. It's going to be on a file somewhere. So if you're storing sensitive information, everyone can read it. And this is a surprising vulnerability in a lot of systems out there where companies are logging very sensitive information that they would encrypt in the database normally. But then when it's not in the database, they just forget all about security. So be careful what you're logging. All right. So I think it's okay to say, okay, Soumya Ray couldn't log in. Maybe this is good for diagnostic purposes later. Maybe later I can say, why is this one user always failing to log in? Is somebody trying to just guess their password or something like this? Okay, but don't store the password in the log file. And you may be thinking, who would do such a stupid thing? GitHub did such a stupid thing. I don't want to say stupid because any of us could make this mistake. But GitHub accidentally recorded some plain text passwords in this internal logs. All right, and luckily, as far as they know, they caught it before anyone else found it. They believe, but they sent out. And this was just this was 2018. It was a few years ago, not too long ago, and they had to actually send out an email to several users saying, sorry, we were storing your password as plain text in our log files, even though we took such great care to hash and do all these things carefully for the actual database. All right. And everyone was like laughing at this in the development community. Goes, oh, how could they make such a stupid mistake? And then a lot of companies quietly turned to their developers and said, are we doing the same thing? And sure enough, couple of days later, 2 days later, Twitter said, oh shit, we were doing the same thing. Just like GitHub. Because they ran an internal audit after they read the news, and they're like, oh, wait, are we doing this? And they said, yes, apparently we were doing the same thing. So sorry about that. Um, so you really have to be sensitive because you may be the person in charge of accounts and you think, yes, I'm taking care of it in the database. But somebody else, maybe on the auth team or some other team, could be handling things and logging things unawares. Okay, so there has to be some internal discussion about what is sensitive and what is not sensitive in an organization. So this is the kind of, so I just want to make a reminder about be careful what you're logging. All right. And yeah, all right. And this is one of the reasons why you need to catch your errors. You need to have those little rescue blocks. Because if you don't have a rescue block and the system just crashes by itself and you haven't rescued it, then Ruby will just print out on to the log file whatever the error was. It'll just print it out, And if that error includes some tokens or this or that, it'll be just all in plain text. So it's important that you rescue for errors, and you also rescue for errors you're not expecting. Maybe just rescue standard error, so you're just catching everything, including things you're not expecting, and you're handling it gracefully. Okay, and you're logging precisely what happened without releasing sensitive information. Whew. All right. Any questions about this? So, not rookie mistakes. Even advanced people make these mistakes as well. Right. So that's API business. Any other API business? Okay. So as we're getting ready to do, as we're getting ready to have a front end, we're going to have people who want to log in, and our API is going to be the one who's going to be saying, yes, they have the right username and password. The API is going to be in charge of authentication, basically. Okay. So one of the routes we want to add this week is going to be for authentication. Just a very light authentication. We're not doing anything too heavy this week, and I'll show you in following weeks. We're going to get a little bit deeper into it. Okay. So so our API is going to be the one in charge of authentication. So whoever it is, the web application or maybe a mobile application, is the one that's going to be sending the credentials to the web API to say, here's a username and password. Does it match? Is it correct? And then the API will say, yes, it's correct, or no, it's not correct. Okay. And so let's take a look at the code for that. So this week I have a auth route. So API/v1/auth. Auth is probably a bad word because it sounds like authorization and authentication. It could be either. But just to be clear, under auth, I have another route called authenticate. So all my authorization and authentication will happen through auth. But within it, I'm clarifying API v1 auth/authenticate, right? And in this route, I'm going to be essentially expecting the other application to post the credentials in, all right? And notice I'm using the post method because when you use the post method, any parameters are sent in the body of the HTTP message, not in the URL, okay? Because, and I know a lot of companies do this, but generally speaking, you should avoid sending credentials, username, and password in the URL itself, all right? Why? Even if you're using some kind of secure protocol, the URL is often put into your log files. Like every time somebody makes a request, the URL is logged. So if people are sending credentials in the URL using a get method, then it's going to be in the log files. Every single username and password will be in the log files. Okay. So to avoid that, we're going to use a post method, and the post method ensures that parameters are not in the URL. They are sent via the body of the HTTP message, which is generally not logged. All right. Okay. So what am I doing? So I'm posting. Then the credentials, the username and password, should come in the body of the request, of the HTTP request. All right. I've created this little helper library down here in my app lib folder. And essentially what this little class does, it just does one little thing, which is it simply takes a hash and converts all the key. Remember hashes have key value, key value, key value. When someone posts something to you, you're going to get, essentially Rhoda is going to convert it into a hash of some kind, okay? And actually not, they're not going to send a hash. They're going to post a JSON blurb with the username and password in there. And we're going to convert the JSON into a hash. And then what this code does here is that it goes through the hash and it converts all the keys into symbols, okay? Otherwise, the keys will always be strings. And just to keep everything kind of similar in my code, I'm going to I'm going to get the JSON that they passed me, and then I'm going to go through that JSON file, map through it. Every key value combination, I'm going to convert the key into a symbol, all right? Then in my code, I can always treat whatever data is coming into me, I can treat every hash as if the key is a symbol. So I just use this little helper to parse the JSON credentials coming in, the username and password, and convert the keys into symbols, and then that's my credentials object. All right. All right, and then after that, please get settled in. And then once I have the credentials, this time the credentials will be a hash with username and password keys. I'm going to pass those credentials onto a service object. We talked about service objects last week. This time I'm going to make a service object whose job is just to authenticate the credentials, all right? The code should not be a surprise. It's pretty easy. The authenticate object basically looks at the credentials, the hash of credentials coming in. It asks which account has this username. And then last week we wrote a little password question mark method in account to basically ask, is the username and password combination correct? All right. And so we just asked this account, is the password correct? If it's correct, please return the account object itself. All right. Otherwise, raise an error. Okay. And okay. And so that's what I'm doing. And if you remember the password question mark method in account, it doesn't like compare passwords because that would be ridiculous. We shouldn't have the password. It basically takes in a new password. It takes in the offered password and it hashes it again to check if it's similar to the hash that's in our database. All right. If any problem happens, you notice here I'm raising a general error. I'm not raising a specific error here. I am then rescuing for whatever kind of error happens. Standard error is the root object of all the error objects in Ruby. So I'm just catching whatever error happens and I'm re-raising it as an unauthorized error. And I've got my own class called unauthorized error here, all right? And the idea here is if something goes wrong in the authentication, this is not the time to stop and say, what went wrong? Did they give me the wrong password? Are they trying to hack into the system? this is not the time to tear that apart and make a calculated decision. If someone's trying to give you wrong credentials, I'm just saying stop unauthorized. I don't care what the problem is. Because if I start adding logic in here about, oh, is it the wrong password or was the username not correct? I'm going to give away information I don't want to give away to the user. Okay? Maybe somebody doesn't even know any passwords. They just want to know, do these usernames exist? So they're just sending in false authentication requests with just random usernames to try to catch a username that exists in my system. So this is not the time to kind of give people a very detailed response of what went wrong. You don't want to tell them what went wrong. You just want to tell them, yeah, no, unauthorized. Okay, wrong username, wrong password, wrong whatever. I don't care, just unauthorized. All right. For this reason, you'll often see when you go to a lot of websites and you're trying to log in, it may say, give us your username and password or email and password, right? And if you enter something wrong, you will notice, hopefully, most websites don't tell you what is wrong. They will just tell you your combination of username and password is incorrect. They don't tell you, oh, yeah, I found the username, just the password is incorrect. They don't tell you that, okay? Because you don't want to give away too much information to the potential attacker of what went wrong. Just tell them unauthorized.
See, it's funny because that means that I have to figure out if my username is wrong.
Mm-hmm.
I'm combining.
Yes, exactly. It is unfortunate for the good users,
Yeah.
but you don't want to give away too much information to the attackers. All right. So for this reason, authentication is not the place to give very sophisticated responses to what went wrong. Just tell them it's wrong. Yeah.
I also noticed another practice recently is that they will send you your user and your password to your email directly.
Yeah, they should never do that. They should never do that. What's that? That means they're storing the password in plain text, or even if it's encrypted, it's not hashed. Okay. So I will tell you, even 20 years ago, let me think. I don't want to age myself. But when I was a graduate student and I first started writing code, I didn't know about any of this stuff. And sure enough, I just kind of stored passwords in plain text. I did it. Okay. And I remember one time getting a really angry email from a user saying, your system just emailed me my password. This is totally incorrect. And I was like, what? Why is that incorrect? I thought I'm helping you. It took me a while to figure out. Yeah, that's really terrible. So we've all been there. All right. Okay. So long story short, we now have an authenticated route and it's a post request, all right? Because GET requests generally are not expected to send any parameter, anything in the body. GET requests should have an empty HTTP body, everything should be in the URL. Post requests expect you to have some stuff in the body, all right? Any questions about this? So now our API has an authenticated route. Yeah, Tara. Yeah, okay, yeah, I'm sorry. This was not a very good explanation. So let me see if I can just demonstrate it. This is the API. Okay, let's just write console. Okay, get into credence. Is my JSON blah 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 thing here? No, it's not. Where is it? API, huh? JSON request body? Why can't I find it? Is it, hold on. Give me just 1 second here, okay? JSON request body. Okay, in fact, it's not even in credence. It's just JSON request body. Let's see how it works. Parse symbolize. Okay, so let me just make a little string here, and I'll just say this is my JSON request. All right, so it's going to be like some hash. Let's say username blah blah blah. Okay, password blah blah blah. Okay, to JSON. All right, so this is my JSON object. Oh, excuse me. Yeah. Notice when I say JSON.parse, the JSON object, I'm going to get this hash back. However, this hash, all the keys are now strings because JSON is actually JavaScript, notation. It's not a Ruby notation. So it doesn't realize that originally, it doesn't care originally that my keys were symbols. Okay. However, in my coding, as a practice, I like to treat all my keys as symbols. Symbols in Ruby, by the way, are just strings. They're just frozen strings. They are immutable strings. You cannot change them. All right. So essentially, JSON request body dot parse symbolize can take a JSON object. It'll parse it into a hash, and then it'll convert the keys back into symbols for me. That's all it's really doing. All right. So I'm parsing the JSON. Then with the parsed object, I'm mapping over it. I'm going through every combination of key and value and converting the key to sim. I do have to tell you, this code is from a couple of years ago. And I noticed in the new version of Ruby and the new Rubocop style, it says, this is a terrible style. This has become such a common practice in Ruby that there is a preferred way of doing this, and Ruby's actually added a method to itself in the past 2 years to do exactly this. So you may have to run Rubocop on this to have it tell you what is the right way of doing it. Rubocop app lib JSON. Let me just Rubocop this one. And you see it'll tell me a couple of errors. But one of them is that, you know what, we now have hashes now have a transform keys object, which you can use to like change just the keys of your hash. You don't have to map through them yourself and extract the keys and da 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 da. All right. I think I believe transform keys is basically going to be a method where you have to provide it a little lambda or a little function to tell it, a little block to tell it how to convert each key. What do you want to do with each key? All right. I'll try to fix that code before I put it up on GitHub, but otherwise, please take a look yourself how to fix that. Right. Okay. Authenticate route for the API. Are you all okay with this? Yes? Question, Tony. I'm sorry. What is the difference between? I'm sorry, Tony, because we're all wearing masks, so I can't read your lips. Oh, routing.is versus routing.on. Whew, good question. Trying to figure this out. Yeah, it's in the Rhoda documentation. The difference is routing.on says is authenticate on the path that I am now trying to parse. So is there an authenticate in it? Okay. Routing.is means this should be the end of the path. So it should end with slash authenticate. There shouldn't be another slash 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 after it. So routing.is basically says, have I reached exactly this path? Routing.on would allow you to have slash more subpaths below it. Does that make sense? Okay. That's a source of confusion for me as well. Okay. And I believe the reason that Rhoda does this, two reasons. One is for safety. Somebody could pass you a route with extra crap in it just to somehow spoof your system into doing something it's not expecting. So using routing.is, you can say end of the road, end of the path, please, nothing more. Okay. So that you don't accept somebody who's trying to hack in some weird way by adding some extra crap at the end. Okay. Um, the other reason is you may have other routing.ons later on, so you can distinguish between the two. But anyway, I won't go more into that. All right. Okay. All right. Web API. By the way, for various reasons, because I use Rhoda so extensively in my classes, I'm beginning to get a little bit of a reputation as the Rhoda guy all the time. And Riley, actually, you applied for an internship, right? At Ruby, what is it called? What's it called? 5 times Ruby. It's like the umbrella organization for Ruby developers in Taiwan. And after did you interview with them? Okay. They asked you about Rhoda, I think, right? They're like, why are you using Rhoda? What'd you tell them? Oh, my professor uses Rhoda, right? Okay, okay, yeah. Well, they were very impressed with your answer, so they contacted me and they said, "Hey, at the next Ruby conference, can you give a talk about Rhoda?" And I'm like, "I'm just a Rhoda user. Like, I'm not like the Rhoda guru here." But apparently, that's becoming my reputation as like the Rhoda guy. So, okay.
Actually, what I saw online is not many Japanese people use Rhoda at all. They use Ruby at all. They use Rails.
They use Rails, right?
Not many Japanese people use Rails.
Not many Japanese people use Rails. They use what?
They use other,
Sinatra, Rhoda,
yeah.
other things. Yeah. Rails, so Ruby was invented in Japan, but Ruby on Rails was was created by a Danish programmer based out of the US, I think, um, and a very, very vocal and famous and notorious developer. Um, but in Japan, they didn't really catch on to the Rails trend. They're like, no, we just like Ruby. So anyway, um, actually, a couple, yeah. Yeah, because Rhoda is a much lower level, so you're doing a lot more work to write this code, and Rails is a lot higher level and it's supposed to be a lot simpler for you. So they're like, if you understand routing this well, Rails should be like you can sit down and learn it in a weekend, you know. So they're like, it's not wouldn't be a challenge for you. Yeah, absolutely. So and the other reason I use Rhoda in my class and not Ruby on Rails is because Ruby on Rails is so unique to how it does things. And I don't want to train you to become just like a Ruby on Rails programmer. I think if you learn Rhoda, then you can use any other framework in Ruby and you can use any framework in any language. You're not like stuck to just Ruby or just stuck to one, one popular framework. So, uh, all right. Okay, so that's controller stuff, and I think that's all I want to say about controller. The big thing being we now have an authenticate route. Okay, and do note if authentication fails on the authenticate route and I catch the unauthorized error, which is the only error that can be raised by my authenticate account thing, then the error code I sent back is 403. 403 is a standard for unauthorized. This is an unauthorized request. Okay. Even if the username is not found, I'm not saying 404, I didn't find the user. No information, unauthorized. Okay. Some companies, as I told you before, like GitHub is pretty famous because when you look for a resource and you don't provide the right credentials, they don't say 403. They say 404 because they don't want to tell you that the username and password was wrong. They just want to tell you, I don't know what you're asking me about. They just want to pretend like it doesn't even exist. All right. Okay. Let's move on. So we're going to be adding a we're going to be adding a web application this week that's going to be talking to our API. All right. And it's going to be collecting usernames and passwords from users and sending it to the API. And this is a huge risk because it's of course going over the internet. All right, it's this request is going over the internet, and we want to make sure that anybody intercepting this cannot read that username and password. So the de facto way of securing your connection between two machines over the web is going to be HTTPS. All right. So this week we want to make sure we're using HTTPS for communications between two machines. All right. Um, I'll just tell you a little bit of the theory behind HTTPS. It's not really relevant to you because HTTPS is designed in a way that you can use it without knowing how the hell it works. But you're in a security class, so you should know a little bit about how HTTPS works. All right. And HTTPS is actually quite transformative to our use of the internet. Without it, we probably could not do a lot of modern commerce and things like that. All right. And it's allowing us now to use the web quite safely wherever we were. Like, again, 15, 20 years ago, if you were in the airport and you were like logging into your bank account or your email, I would say, stop, don't do that. You're on a public network. It's crazy. Though it's a crazy world. But HTTPS has evolved and become quite a bit secure, and we're now quite confident. And now people are in security blogs are saying, you know what, go ahead, use that hotel Wi-Fi, use that airport Wi-Fi, no problem. Okay, because the protocol has become more mature and it's become quite usable, so that you can actually use the internet wherever you want if you have an HTTPS connection. So, um, and not only that, it's web browsers are also beginning to take HTTPS very seriously. In 2014, in fact, Google started using the fact of whether a website is using HTTPS or not as part of its ranking algorithm. So if you have a website that is not using HTTPS, Google ranks you lower in the search results because they feel you really don't know what you're doing. All right. So that was 2014, and that like woke a lot of people up. They said, "What? Hey, go to HTTP." Even managers who don't care about security are like, "Oh my God, our our SEO is going to get hurt. Let's switch to HTTPS." So it was a great motivation for many people to switch to HTTPS. In 2018, Chrome again led the way, I think, by saying that if your website is not HTTPS, they're going to like put a label on your website saying this is not HTTPS. All right. And it's going to say not secure. And now all the popular browsers do that. Firefox, Safari, Chrome, they all add a not secure tag next to the URL if it's not HTTPS. Okay. Shamefully, one website that I am going to ask you to look at this week does not use HTTPS. I think it's Slimlang. This is a framework for Ruby, but I'll just it's an HTTP page. Yeah, and Firefox just tells you not secure. I think Chrome or Safari writes out the words not secure on it. And I'm actually hoping in near future, I am expecting browsers will just stop you and say, do you really want to go forward with this or not? Okay, so expect that coming up soon. It's an optional feature in Firefox already, so you can, is it turned on or turned off by default? But you can turn it on and say, don't let me in, right? Okay. I actually have is it on my Firefox? On my Chrome, or where is it? I don't know where it is. I've got too many plugins. Um, in my, I forget, in one of my browsers, I've got a plugin that basically says, if I type in HTTP or if I click a link that takes me to HTTP, it first reroutes me to look for an HTTPS version of that route. So I've got a browser plugin that stops me from using HTTP if possible. All right. Okay. So how does HTTPS work? It's a I think a lot of users take it for granted that this kind of magic exists, that I can just go to a website and suddenly, bang, we are communicating privately. Like, how? How does that even possibly work? All right. And as you're going to see, it's not a magic of technology. Well, it is. It's using the cryptographic technologies we've studied in the class so far, asymmetric key encryption and symmetric key encryption. It uses both. But you'll see it's also a very fine balancing act of trust. And I talked about this, I mentioned the word trust a couple of weeks ago in the class when I said you're going to find the security is really a story about how do we trust anybody and how do we transfer trust. And you're going to see that in quite a bit of detail right now. All right. So first of all, what's happening when you go to an HTTPS page? What is it that makes HTTPS secure? Give me one thing. What is it that is so secure about HTTPS? It's end-to-end what? Encrypted, right? So basically, I go to a web page and it's encrypted. We're talking in an encrypted channel, right? Wait, is the data being sent to me? Is the website data and my communications, is it encrypted using symmetric key or asymmetric key encryption? The data. Asymmetric? What did I mention a few weeks ago about asymmetric key encryption? It's too slow. You can't actually use it to encrypt data. It's never used to encrypt data. What is it used to encrypt? Keys. It's used to encrypt symmetric keys. So no, the communication is not encrypted with asymmetric encryption. it's using a symmetric key encryption because it's fast. All right. Otherwise, we can't stream Netflix. All right. It'll be like ridiculous. Can't even have a web page show up in real time. So it's encrypted with symmetric keys. But how are we exchanging the symmetric keys? Using asymmetric key encryption. All right. So they have a public key and a private key. I have a public key and a private key. And we're exchanging public keys. We're using our private keys to encrypt and transfer the symmetric key. And then the symmetric key is what we use to communicate with each other. All right. So just a reminder again, we do not use asymmetric key to actually encrypt data. It's infeasible. So we use symmetric keys. Okay. Great. Wait, hold on a second. How are we getting their public key? Like, do they just send us the public key and we go, okay, I believe you? How do I know somebody didn't intercept it in the middle and change the public key? That'd be really easy to do. Like I see two people talking and I'm the man in the middle. So I see two people talking and I see a public key going and I can just whoop, take the public key away and send my own public key. And then I have kind of hijacked the conversation, right? Because then they are trusting me where they should be trusting the other person. So how do they possibly send the public key over? Or what's that? There's some kind of signature involved. Okay, so let's talk about this for a second. Um, so um, remember that digital signing, remember this concept? Where if you want to convince somebody that you are the one communicating with them, what you can do is you can sign some information using your private key. And then the other side will use your public key to undo that encryption. And they'll say, oh, okay, it was obviously encrypted with the private key, so it had to be you, the signer, who sent this to me. Okay? We call that digital signing several weeks ago. All right? Now, here's your public key. Okay? But the question is, how can Bob know that they have Alice's public key? How do you get that public key safely and securely? We didn't discuss that before. What I told you is go to a Starbucks and exchange it in person. How do we do it in this class? In this class, I asked you to put a fingerprint of your public key on your spreadsheet, right? And I think you've probably noticed by now that each tab in that spreadsheet is limited to just you and your teammates. So nobody outside your team can write into your tab of your Google spreadsheet. Okay? So that way, I can be kind of convinced that either you or maybe one of your teammates, but hopefully just you, actually put that fingerprint up there. Okay? And I know it's you because I'm using your email address to block anybody else from writing into that spreadsheet. So the reason I trust you to put your fingerprint up because I trust that I have the correct email. All right? And I trust I have the correct email because it came through me through the school system. So that's how the trust was transferred. I trust you, but I don't know who you are, but I trust that the school has authenticated who you are somehow through a lot of paperwork, and you provide your email to the school. Then the school, then I get your email from the school and I block the Google spreadsheet to your email. And now I trust that whoever is entering information on this Google spreadsheet is you. So essentially, it was a game of trust. I don't know you, so I trust the school. And I believe the school trusts you because they've done a lot of paperwork with you and made sure they got the right email for you. So then I indirectly trust you through the school. That's how I set up my trust with you. All right. How do you do that with just some random website out there? You say, hey, you've got to be a student at NTHU. How do we do that? How do we accept their public key? So this is a huge problem. All right. And the way we do it is something like this. I cannot trust some website out there. And security at the end is a game of trust. We have to trust somebody who trusts the final website. So what we do is this. We all find somebody who we trust. And typically, this is a company or an organization or a person who we call a certificate authority. It's somebody that we all agree we trust that person. Okay? Who that is, I'll talk about in a moment. But let's assume for a moment, maybe it's God, I don't know. But let's assume there's some divine power that we all trust. Okay? And what we're and what we're going to do is we're going to ask this certificate authority, the person that we all trust, can you please give us your public key? All right. So I don't trust, let's say Stephen. I trust Stephen. Let's say I don't trust Stephen, but I trust the certificate authority. And no, your name begins with E. I can't trust you. Sorry. But I trust Riley. You got two names. Yeah. That's even more suspicious. Like, that's exactly what an attacker would say. All right. Um, yeah, exactly. Can't trust any Latin Americans. That's terrible. But let's say I trust Riley, okay? And I say, Riley, I don't know Steven, but I trust Riley. So I say, Riley, I have your public key through some other methods, okay? And then Riley's job to learn who Steven is and to trust Steven, okay? And to trust everyone in this class, in fact. So in future, when I need a public key from somebody, I say, can you please tell me who you are, your identity, and can you please send me your public key, Stephen? But I need Riley to sign this whole document. I need Stephen's public key and Stephen's identity, name and email, all of this signed by Riley's private key. Because that shows me, so if you give me this, Stephen, then I don't have to contact Riley. I can just use Riley's public key to unencrypt this, and I can go, oh, this was signed by Riley, and I trust Riley. And Riley trusts you enough that she has used her private key to encrypt this. All right? So this is the transfer of trust. How do I get someone's public key? I say, please send your public key to a certificate authority, get them to trust you, and when they trust you, ask them to sign your public key with their private key and send me that signed document. That signed document, a document which is signed by a certificate authority using their private key and contains your identity and public key, this is what we call a digital certificate. Okay? So a digital certificate is basically your public key signed by somebody I trust. Ta-da! That's at the heart of HTTPS. All right? And it's at the heart of a lot of secure protocols. Okay. So long story short, when we start communicating, I need to have the certificate authority's public key. That's what I need to begin with. I need to have, let's say Riley's our certificate authority. I need to have her public key. Now, anyone can communicate with me, but they need to send me their identity and public key signed by Riley. Got it? Any questions about this? Are you okay with this? Okay, cool. Now, the question is, who is Riley? Who's the certificate authority that we can all trust in this world? And this is a human problem. This is not a technical problem. All right. This is a trust problem. We don't trust anybody. There's several different. By the way, this whole setup that I described here with like having a certificate authority, signing other people's public keys, etc. This is sometimes called PKI or public key infrastructure. It's how we it's kind of the mechanism by which we can exchange public keys. Okay, but we haven't solved the problem of who is the certificate authority we trust. So PKI comes with many trust models, like who do you trust? One obvious trust model is the whole world should trust one certificate authority. I don't know who that, United Nations or somebody. Like there has to be, the one thing we could do is have one certificate authority the whole world trusts. Okay. However, that's a little bit of a problem because there there is no such person that we all trust. Okay. Um, so this idea of having only one certificate authority is kind of untenable because there is no such person that we all trust. If there was, this model would be called a monopoly model. There's only one person who we all choose to trust. Okay? All right. Another possible, but this is not reality. The monopoly model, generally speaking, does not exist unless you're within a single company, and then maybe the company can act as a certificate authority, and all the people within that company can ask for public keys signed by the company. All right. So if you're doing something within an intranet or within a local organization, you can use this kind of a model to exchange public keys. All right. For example, NTHU could say, hey, when you become a student or faculty member here, you must create a public key and a private key. And in the paperwork, you must give it to them, and they will sign it. And then everyone within NTHU can know your public key signed by NTHU. That could be an example of an organizational level PKI, public key infrastructure trust model. All right. And so within small organizations or large organizations, even, you can have a model like this. Okay. However, what do you do if you are distributed and everyone doesn't know who to trust? Another possible model is called a hierarchical model, where everyone trusts their own certificate authority. Okay, so let's imagine like we had this model, the monopoly model first, where in NTHU, the school has signed everyone's public key. Fantastic, okay? But now, what if I need to communicate with somebody in Jiaotong? That'll be a problem, okay? Um, what do you call Jiaotong nowadays? And something short, NYCU? NYCU. So you need to talk to somebody at NYCU, not NTHU, NYCU. Well, now there's a problem because I don't trust their public key. And NTHU doesn't know them. It doesn't know anybody at NYCU. Apparently, we don't talk to each other. Okay? It's the funniest thing when I came to Taiwan. It's like, I don't know. I don't want to get into it. It's like, um, so, yeah, tribalism. So one model we could do is NTHU could be a certificate authority for everyone in NTHU. NYCU could be a certificate authority for everyone in NYCU. And then these two certificate authorities could agree on a third person they all trust, they both trust. Maybe it's Taiwan, maybe it's Ministry of Education. All right, they have to trust Ministry of Education to get their funding from there, so they trust Ministry of Education. So Ministry of Education could be like the big certificate authority for the smaller certificate authorities. And now, how do I trust somebody here? Well, I trust this person, and this person trusts this person. So that's how I learned to trust this person. Okay. So I basically asked my certificate authority, can you give me a signed document for this user in NYCU? And they ask the root certificate authority, hey, can you give me this person's, right? It goes like something like this way. This could again happen, let's say, between some organizations that are dealing with each other, potentially. Maybe this is a company, this is another company, and they've hired a third company to do this, to have this kind of trust between them. Okay. This is all great if we are within organizations and companies, but what if we're just on the internet? We don't like, we're not part of any organization if you're just an internet user. So what do you do? On the internet, we use a third type of model called an oligopoly model. And in the oligopoly model, the way it works is there are many certificate authorities, not just one, and there's no ultimate root. There's just several certificate authorities, and like it or not, we have to learn to trust all of them. And if you don't trust one, well, then you cannot communicate with users of that certificate authority. So the modern kind of security model on the internet is there's dozens of certificate authorities all around the world, which are typically companies, and we all agree to trust those companies. And if those companies screw up, we stop trusting them. All right. So who are these certificate authorities in the world, in the real world? Here's a list. Here's a short list from 2011. All right. So in 2011, when I started teaching this class, the number one certificate authority was Komodo, and then Symantec, GoDaddy. Do you know any of these companies from other than being a certificate authority? GoDaddy is famous for what? Apart from really bad advertisements. Um, so yeah, they're domain name hosts, right? With a lot of interesting marketing. Anybody else recognize any of these other companies? You're too young. Symantec was really famous. Yeah, it was one of the most famous antivirus companies. It was. Well, I mean, it still is, but people don't use antivirus that much anymore because your operating system comes with an antivirus built in. So, but Symantec would made their name with that, but now they're a certificate authority. Okay, because we trusted them with security back in the day, and people just maintain that trust. Okay, so these companies are the companies that have kind of gained the trust, and you'll see they're quite heavily used. They all have pretty significant market share. And if you look in your, I don't know where it is, but actually, these certificate authorities are not only trusted by your browser has a list of certificates. So when you download a browser, the browser comes with certificate authorities, public keys built into it. So when you download Firefox, Chrome, it comes with certificate authorities built into the browser with their public keys. So you don't have to know them personally. Your operating system also comes the same way. Your operating system comes with certificate authorities that they trust already. Okay. So when I open up the keychain on my Mac, these are all certificate authorities who are listed. My God, this is a huge list. Who are listed on my operating system as certificate authorities that at least Apple trusts. Okay. So my browsers, if they wish, they could also use these certificate authorities if they wanted to. Okay. So, and of course, Apple is one of the certificate authorities that Apple trusts because it's Apple. Okay. But Amazon has its own certificate authority. It can act as a certificate authority as well. Not one of the most popular ones, but they have their own service to act as a certificate authority, right? And some of the others you may not recognize their names. Komodo is still in here. It's still in here. Okay, etc. However, how do you trust these certificate authorities? Like, why do we trust them? It's just a human story. We trust them because they haven't screwed up yet. And as long as they do a good job of getting people and certifying them, we trust them. But there's a slight problem here. How, if you're a new company and you need, private key, public key, you need a digital certificate, what do? Well, you have to go to one of these companies and prove to them who you are, and they will give you digital certificates. All right. Well, how do they get to know you? The way it's typically done is you pay them it's a service. You pay. That's how they make money. You have to pay them, and they will do some procedure to get to know you. Maybe they'll say, "Hey, let's look at your credit card number. Does it belong to does the bank authorize that it belongs to this company, etc., etc." They have some procedures, some financial procedures to verify who you are. But there's something a little weird here that I got to mention, which is there's a weird perverse incentive here. You are paying them to trust you. If they don't trust you, then they can't get your money. So this is a little weird. um, they're incentivized to trust you because otherwise they can't make a profit. And this is the problem with the oligopoly model. Okay, sometimes they slip up because they're not careful enough because they're incentivized to be not too careful. They're playing a fine game. They're playing a financial, a corporate game where they want to do just enough due diligence to trust you, but not too much to piss you off. So they don't go all the way to trusting you. They just do enough to get your money and say, here's your digital certificates. And we knew this is a problem because if you pay them enough, they will trust you potentially. All right. And sure enough, in 2011, some hackers from Iran, apparently, could be from anywhere, but this time from Iran, they managed to fool Komodo to certifying that they were Microsoft. So they got a digital certificate from Komodo saying, we are Microsoft, and they're a bunch of hackers. And they use this to kind of infiltrate networks and convince people like, hey, your Windows is out of date or something like this. Please update it. And Windows will say, hey, are you Microsoft? And they say, yes, here's my digital certificate. And they were able to hack into a lot of systems using this technique. All right. So, so what happened then is people all said, what the hell's Komodo doing? They're the number one certificate authority, and they screwed up. So in 2021, if you look at the list of top 415, Komodo is not on there anymore because a lot of browsers simply said, we're going to drop this certificate authority. We don't trust it anymore to do a good job. All right. So hopefully that's a display that the market works, but it's also an example that hackers can exploit the market quickly just one time. All right. So it's a careful balancing act, but today these are the most popular certificate authorities. Number 10 is probably the new kid on the block, and it's really famous. That's Encrypt. They don't take any money whatsoever, and they have a fairly straightforward and easy way to get certificates from them, and anybody can do it for free of cost. Okay, but it was kind of a response to all these companies making a lot of money and having the wrong incentives. Okay, so this is the story of certificate authorities. They're already in their digital certificates with their public keys are already on your computer. All right. So this way, when you go over the website and you go to a company's web address, that company has to send you their public key, but their public key has to be signed by one of these certificate authorities. All right. And if you choose a certificate authority that's not very popular, then you run the risk that on the browser, have you ever gone to a website and the website blocks you and says, stop, we don't know who this person is. They give us a digital certificate, but it's not by a certificate authority we trust. You will sometimes see that error message. Okay. So this is HTTPS, and I don't want to go into too many more details, except the HTTPS protocol basically starts with an exchange of certificates. Right? Your browser says, here's my public key, and the company you're trying to contact says, here's my digital certificate. It's signed by somebody you should trust. All right. And then you exchange private keys. It's not private keys, holy shit. You exchange public keys. So this is all done with asymmetric key encryption. Okay. And then the last thing is that the server on the other side, the company, once you've trusted them, they generate a symmetric key. And they send that over to you using asymmetric key encryption. Right. And then you agree on which cipher you're going to use. Okay, we're going to use AES or ChaSha20 or whatever it is. And then the encrypted data is sent back and forth using regular symmetric key encryption. Okay? So that's, in a nutshell, that's how HTTPS basically works. Okay, it's public key infrastructure, digitally signed public keys, which we call digital certificates, which you use to then exchange symmetric key and agree on the cipher that you're going to use. And then all the encryption happens with symmetric key crypto. Excuse me. Any questions on this? Please. Yeah. Yes, it is. And your browser should take care of that for you, so you don't have to do it by yourself. Okay. So your browser should have a mechanism to talk back to its parent company, Firefox or Google or whoever it is, and say, hey, I need to update these certificates. Okay. And also, every time you update your whole browser, it comes with new certificates, very likely. Okay. But you'll notice if you looked at my keychain, a lot of these certificates are valid until like 2030, 2038, like way into the distance. All right. Okay, cool. What's next? So, what? Since now you know a little bit about crypto, about different types of asymmetric key and different types of symmetric key crypto, what ciphers are they using? Like, what algorithms are they actually using? Because we looked at a few in the class. right? Because in this class, we're pretty picky, right? Like, who do we trust? It's DJ Bernstein, all right? So whose ciphers are they using? Um, until recently, they were using largely ciphers like AES, which we studied in this class. You even saw a little video about how it works, okay? And several others. And if you look at the different versions of the secure protocol, so by the way, the HTTPS, the actual the crypto part of the protocol is sometimes called SSL, but lately it's changed name to TLS. Okay, Transport Layer Security. And in older versions of HTTPS, which were using like SSL version 2, version 3, I can't remember what they were using. They were using like IDEA, DES, RC2, all this stuff. But these are all now shown to be insecure, so we've stopped using them. Currently, people should be using TLS either version 1.1, but mostly version 1.2, and we're now transitioning to version 1.3. And most of these algorithms are no longer trusted. AES is still trusted, right? AES is still trusted as a version 1.3. However, some versions of AES using like, remember CBC cipher blockchaining is no longer trusted. So some modes are trusted and some modes are not trusted. And a lot of these are not trusted. Oh, look, there's one more down here that is trusted. Who could that be? It's our good friend, DJ Bernstein's Cha-Cha-20 Poly 1305, exactly what Simple Box Secret Box uses. Remember, Cha-Cha-20 is the symmetric key cipher. Poly 1305 generates the authentication block, the hash block, if you will, that goes along with it. Okay. So remember, when we use Secret Box or Simple Box, it's doing an authenticated encryption. It's encrypting the data, hashing it, and producing a hash block as well. The hashing algorithm uses the same key as the encryption algorithm. All right. So encryption, message authentication block, or MAC block, or the hash. Okay. Cha-Cha-20, Poly 1305. So moving forward, this tends to be like the favored one. AES is still trusted in some modes, but you can really see this is beginning to take over everywhere we look now. Right? All right, all right, all right. And so there's still very few people using the old versions of SSL, the old versions of TLS. We're mostly now on TLS version 1.2, and TLS version 1.3 is taking over, where only two types of AES and Cha-Cha-20 is trusted now. Okay? So I'm not going to go say further, except our applications, we're going to have our own digital certificates this semester, but I don't want to take the time to apply for one because it's a process and each team would have to apply for your own digital certificates. Instead, we're going to use a cloud provider this semester, Heroku. And basically, if you use their domain name, like if you allow your deployed, we're going to deploy it later this semester, but once we deploy on Heroku, if you deploy it and allow them to use their domain name, so it'll be your application.herokuapp.com, then you can use their digital certificate. Heroku will give you their digital certificate to send to users. Okay. Yeah.
Should we use Heroku?
We're gonna use Heroku. Yeah.
If not,
If not what? Um, try using it for this class. When you've outgrown it, you can use something else. Okay. Outgrown it meaning when it's too expensive. But they take care of a lot of stuff for you. They'll be the ones securing and patching your operating system, ensuring the security of all these other services around you, et cetera, et cetera. So trust them as long as you can.
so what's the have you heard about Netlify?
Yeah, I use Netlify for my own website.
So how is it different than Heroku?
Netlify is great. I use Netlify mostly for static websites, not for like dynamic websites where I'm running code. All right.
So
So
dynamic, I should use Heroku.
you can use whatever you want. I will recommend you start with Heroku, particularly because it's free in the beginning for limited use. Okay, for limited use, it's free, so you can start getting get your application working. If you don't want to pay their cost, then you can switch to somebody else. Actually, Heroku doesn't have their own machines. they're running on top of AWS. So actually, all our stuff is going to be hosted on Amazon, but Heroku just manages it all for you, updates the operating system, takes care of the database, you know, secures the database, applies the latest patches. They do all this kind of systems operational stuff for you. All right. It's just that once you start becoming a real company and you have a lot more need more resources, they become very expensive very quickly. Okay, but for this class, it'll be free in the beginning with certain constraints, which we will see later. Okay, but I do know companies that are using Heroku and they have like I don't know, like tens of millions of users or hundreds of millions of users even. Okay, it's just that it becomes very expensive. But the reason we're going to use them is if you're a company and you really want to do everything yourself, you'll find that if you want to hire really professional people to do this kind of operational stuff, it's a lot more expensive than paying Heroku. Like hiring a real database administrator, hiring a network manage administrator, hiring your own security people is a lot more expensive than paying them. So they can charge a lot of money because they know how much professionals really cost. So they just charge you a little bit lower than hiring your own people. Okay. But if you hire your own bootleg people, then it's cheaper. But you don't know how talented they are. Okay. All right. Okay. So long story short, we're going to use HTTPS, and we're going to save ourselves a lot of effort by simply using Heroku's public digital certificates. Okay. Now that is when our machine is deployed, when our server is when our application is deployed. We haven't deployed it yet. We're still in development mode right now. And in development mode, I'm not going to have you set up a digital certificate because it'll be too painful to do just for development. Okay. So what we're going to do is the following. This week, we are going to insist that all communications to our web API are secured. All right. And let me kind of show you how we're going to do that. All we're going to do is this. In our API's controller, when we start routing, so this is the beginning of our routing block, right? A request comes into our API, we go through the routing blocks. At the very top of our routing blocks, after we've kind of said, well, this maybe should even come after, but one of the first things we're going to do is we're going to check this routing object, and we're going to make sure that the routing object, this contains the URL that's being requested. It also contains the method like get or post, and it also contains the HTTP scheme. Is it HTTP or HTTPS? And we're going to simply check, are we doing HTTPS or not? I've written a method that I'll show you in a second, which basically asks, is this route on a secure protocol or not? If it's not, we're going to halt with a 403 and say, please, you need to use HTTPS or TLS to access this web API. Okay. Where's my code for secure request? Did I not show it to you? Oh, I didn't even put it here. Huh, funny. Let me just let me just secure. So it's right at the. I think it's in one of my slides, but I forget which one. Oh, it's right here. Sorry, it is on the slide. Before all my routes, I just define a little method called secure request, question mark. It takes the routing object from Rhoda, and then it opens up the routing object and asks, what scheme are you using? Scheme is going to be either HTTP or HTTPS. And I simply ask, does this match the secure scheme that is stored in my secrets.yaml? In secrets.yaml, for production, the secure scheme will be HTTPS. For development and testing, I'll keep it as HTTP, so I don't need a digital certificate during development time. Okay. And so that's all I'm doing. I'm just asking, are you HTTP or are you HTTPS? And if it's the correct scheme, I return true. Otherwise, I return false. All right. And if it's not the correct scheme, I throw a 403 error. All So all I'm doing in my API now is I'm asking, is this request coming to me by HTTPS or not? Okay. I got a quick question for you. There's an alternative to this approach. The alternative is if somebody sends me a request to my API via just regular HTTP, instead of rejecting them, I could reroute them. I could say, hey, please come back to me on this address, and I could give them an HTTP address, right? That way, it wouldn't break the communication we're having. It would kind of go very naturally. Like they would make a request and it would automatically reroute them to an HTTP address, HTTPS address. Is that a good idea or a bad idea for an API? Tough question. Should I just tell them, hey, here's the HTTPS version of the request you're making. Please come at me through this address? Or should I just reject them and say 403 unauthorized? Why not just reroute them? Reroute them. Be nice. The only issue I have with rerouting is that it's possible somebody's making a request to me. And for example, it could be with user credentials, like username and password. If I reroute them, then they don't learn that I need them to be HTTPS. Okay. For the API, I'm going to be rejecting them so that the developers on the other side are made very aware that you cannot be sending me credentials and other sensitive stuff by regular HTTP. I will not be accepting those requests. If I do a reroute, they don't have to change any code. A lot of modern packages for HTTP communication will automatically handle the reroute. So they will never learn. They will keep sending me stuff on HTTP. It'll automatically get rerouted. They will never change their code. Okay, and that's really insecure because their first request is always an insecure request. So I'm deliberately blocking them so that they have to modify their code and always send me first an HTTPS connection. All right. So that's kind of just my approach to security. Yeah, Riley.
Does the reroute take some cost?
It does because you basically have to reject them and they have to make another request. So there's two requests instead of one.
So maybe the cost may hurt the API?
It might, but it's not that big a deal. It's not that big a deal. To me, the bigger deal is that they will keep sending me HTTP requests in future because I'm automatically rerouting them. They will not change how they're communicating with me. And they will be sending me sensitive stuff by HTTP every single time. So that's why I want to put a stop to that practice and say, nope, I do not handle anything that is not HTTPS. Okay? All right. Okay. Let's take a little break and we'll come back and we'll start working on our web application. All right. So let's just take about 5 to 10 minutes and we'll come back and we'll get going on the application.